Let me just check. Yeah, we can get started. So, few announcements. I will be on a conference travel, two back-to-back conferences. So, September 18th, 23rd, and 25th, there will be no class. You have a project due, which is what is the topic that you want to investigate. So, that is due on September 18th. So, hopefully, you will use that time constructively to figure out what is it that you want to do for the course project. And I'll be uploading an assignment 2 today, so you can spend some time doing those assignments on September 23rd and 25th. And please also make some progress on the project, so that way, if you have any questions, you can feel free to ask me after September 25th. Okay, so I will be out the entirety of these 3 dates, so I won't be able to answer your questions uh, or be able to respond to any queries you might have on those dates, but feel free to reach out to me and I might respond to you over a weekend or something. The other announcement is, in the previous class, thanks to Phil, I made a mistake in the previous class, and thanks to Phil, I just wanted to point it out. So if you go back to the YouTube video at 24 minutes 54 seconds, I had written this statement. So the correct statement is, there is a T operator acting on V here. So this is TV plus K1S equals to TV plus KS. Now V star, if V is a fixed point of this, so if V star is fixed point, then TV star plus K1S equals to V star plus K1S. So this statement holds only for V star, but not necessarily for arbitrary V. But for arbitrary V, this statement holds. And I think in your assignment 1, either you have to prove this result, or maybe you have to prove it in assignment 2. But there is one assignment where you will have to establish this result, so you will have an idea of, yeah.
I thought this operator doesn't have a fixed point, and that's why we can't use.
Well, it doesn't have a unique fixed point, but it has like a whole.
The thing that has a fixed point was the operator, and then minus the ones vector times the reference.
No, that's a representative element of the quotient space. But so it has a fixed point in a quotient space. So yeah. So
because last time you said k plus 1 equals t dk.
Will diverge to infinity.
Yeah. You said that thing converges to u star. So that's not just t. That also has the kind of correction.
It has a so what I mentioned in the previous class is vk plus 1 equals to t vk. This goes to infinity. So this one diverges to infinity. So what we want to do is make sure that we get a finite value in the limit. So what we do is pick a reference state and then subtract the reference state from tvk at all points of time. So this is the relative value iteration. So this one, what this iteration converges to is a v star, which is not a fixed point of t. I mean, okay, so
yeah, that's my point.
Yeah.
If I set k equals 0 in that equation in the box,
right,
then that suggests that the regular iteration doesn't go to infinity.
Yeah, so maybe I should write it in this fashion. So there will be, okay, well, I want to write it in a specific way. So v star plus k plus g, I think, g star. Yeah, that would make sense.
I believe that.
That would make sense, yeah, definitely, yeah. So t, yeah, so let's write that t doesn't have a fixed point, but t has a fixed point in a quotient space. So, but anyways, I don't want to talk about quotient space. So this is what it's going to look like for the fixed point. This g star is a scalar, this is a scalar, this is a unit function, and this v star is of course the function itself. So that's the correction you have to make in the previous lecture's content. Any questions from the previous lectures? Yes.
Why did it converge to diverge to infinity?
So remember that it doesn't have a discount factor alpha equals to 1. So each time you're adding a cost, right? And that cost will just keep adding up and it'll go to infinity. Okay. Any other question? Yes.
Is the cost necessarily positive or non-negative? Because if you have negative costs, that doesn't necessarily happen.
Yeah, so if you have negative cost, then it will go to minus infinity.
I mean, the cost average to zero, then it's actually stable.
Average to zero under what policy? So it won't average to zero under all possible policies. Yeah, but
Under a given policy.
if it averages to zero and if that's the optimal policy, then I guess again you will have a similar situation where it will go to zero. But generally, those are rare instances and it doesn't happen in generic cases. And especially because we are talking about cost, typically costs are always positive. Typically, it doesn't always have to be positive, but typically costs are always positive. So what I meant to say is that it is going to diverge. So it could go to plus infinity if costs are positive, it could go to minus infinity if costs are negative. But yeah, I don't want to write all those different terms and conditions. But you have to apply your judgment as to where this will diverge to plus infinity or minus infinity, depending on whether the cost is positive or negative. For sure. Any other question in the previous class? We are going to start a new topic today, which is policy iteration algorithms. So if there are no further questions, I'm going to erase everything from the board. Policy iteration algorithms. Okay, so we talked about value iteration algorithms so far, and we showed that under the case of discounted case, value iteration converges. In the case of average cost case, we didn't really show it in the class, but there are results available that you can refer to. So in the case of stochastic shortest path problem and in the case of average cost problem, under certain conditions, value iterations converge. And the proof of value iteration converging always relies on Banach fixed point theorem, which is something we've studied. And the only difference going from one algorithm to another is under what metric Banach fixed point theorem is, the value iteration operator is going to converge, or Bellman operator is going to converge. So policy iteration has a slightly different philosophy than value iteration algorithm. So let's see what the policy iteration algorithm says. So there is an actor and there is a critic. By the way, I don't know why these names were given, but anyways, people like to come up with names. So this is known as an actor-critic framework. So the actor spits out a policy, mu, and the critic spits out a value, v, or j, j mu. So depending on the context, you will have exactly j mu, or you might have some other value v, which is fixed point of some other equation. Okay, so the critic sends this function v or j mu back to the actor, and the actor performs what is known as policy improvement step. And then after doing the policy improvement, it spits out a policy mu, which then goes to the critic, and the critic does policy evaluation. And so we keep going in the loop. So we start with some policy mu naught. We send it to the critic does policy evaluation, sends us j mu naught or v0. Then it goes to the actor does policy improvement on this particular function v naught, and then it spits out mu1. It goes to the critic sends v1. It goes to the actor, and this process continues for forever until it converges to a specific policy, mu star. Yes.
So is this an alternative to dynamic programming? more general, you can apply it when.
Yeah, so there are policy iteration algorithms that would collapse to value iteration under certain specific parameters. So for sure, you can think of it as a generalization of value iteration algorithm. Okay, any questions on this? The only thing that, so this particular framework relies on what I would call a rollout algorithm or a rollout step. So I have a policy, given policy mu. My cost is, or my value function is, V mu equals to J mu I0, so V mu I0. So you start with I naught, you apply this policy mu, you get a value V mu, which is a function of the initial state. So I'm given a policy mu, I can compute the value function of V mu, and then I define this new policy mu plus as the argmin mu plus I equals to the argmin of u in ui summation piju c plus alpha v mu. And the theorem is that V mu plus is less than equal to V mu. So component wise, V mu plus is less than equal to V mu. In other words, V mu plus I is less than equal to V mu I for all I in S. Yes.
So like on this C in the argument step, that's a function of U.
So C is a function, cost is a function of I, U, J, and whenever I'm picking a specific U, that U will get applied here. So this, you want me to expand on this? Yeah. So this is a function only of J, and this is a function of I, U, J. And alpha is the discount factor. Any question? This is the policy improvement step, yeah. Any questions so far? Okay, let's see why this result is true. So I have a particular policy mu and I have the corresponding value function. I do one step improvement. Okay, so I'm doing the improvement in the policy by applying this particular operator, and I'm coming up with a new policy mu plus, which is my next policy. So this is the policy improvement step. This is what we will be using. So this is the operation that the actor does. It goes from V to mu plus. Okay, that's what the actor does. We haven't talked about policy evaluation yet, which is what the rest of the lecture is going to be about. But let's look at what the actor does. Actor takes as input a value function and it outputs a policy mu plus based on that. And it hinges on this result that whatever value you get out of mu plus is always going to be better than the value you get out of the policy mu.
So you should set up a email to start up this cycle.
You can start anywhere. You can start with mu naught or you can start with v naught.
But you don't have the email, so you can't perform the admin.
Yes and no. So this result is a bit more general. I'm of course talking about it in the context of vmu, but
So where's vmu?
sorry.
So where is the vmu? How can I get vmu?
Well, then in that case you can start with a specific policy mu naught, and you can get v mu naught. Okay, but what I'm saying is this result will hold for all. It'll hold for all v's, but I'm just proving it for v mu. Okay. See, a lot of the results that I'm going to talk about in the class, because I have to prove it in the class, is going to be easier to prove. But then you can go back to the references and you can figure out what the most general proof is going to look like. Okay. Any other question? Yes.
This premium clause means that plugging mu plus to that equation, right?
Right. Plugging mu plus. So remember, once you pick a policy mu, in order to compute v mu, you have to do infinite number of iterations, right? You have to evaluate the value function with respect to that particular policy. So that's an infinite number of iterations that you have to do. So this v mu plus is the value with the policy mu plus. Okay, this v is a value with the policy mu. Okay. So let's look at what this statement means. So what is v mu of I? So this is C of summation of j in S, C of I mu I j. No, I need to take the, let me take the expectation. Let me take the expectation. Let me write from the first principle. So let's not jump ahead. So this is expected value of summation t equals 0 to infinity alpha raised to t, C of it mu of it, and then it plus 1. Right? We all agree on this? Yes.
Given I0 is up.
Given I0, that's right. Yeah. I want to simplify this. I want to write it in a vector or a matrix format. So what should I do? Let me define C mu of I to be summation j in S, P I j mu I, C I mu I j. And let me define P mu. This is capital P mu, and the ijth element is equal to Pij mu I. And again, if mu is randomized strategy, which it won't be here in today's class, but subsequent classes, sometimes mu could get randomized, then you have to take another expectation with respect to mu, which I'm not writing here. Okay, so I define a matrix, so I define a vector C mu. So ith component of the vector is defined in this particular fashion. So I'm taking the expectation with respect to the future state evaluated at the current state and the policy and the action mu of I, right? So mu of I is an action, right? The policy maps state to action. So this is an action, this is an action. Similarly, P mu ij, so P mu is a big matrix. It's a n cross n matrix. The ijth component of this particular matrix is given by this transition probability. Pij evaluated at mu I. Okay, so what does this expectation then, how do I write this particular expectation? So this is equal to the expectation of Ci 0 mu I0 I1 plus alpha C of I1 mu I1 I2 plus alpha square C and so on. And I'm taking the expectation with respect to this entire transitions that are going to happen in the future. I naught is equal to I. Okay, so I'm going to condition it here that I naught is equal to I. Okay, so can I write it? How should I write it? I think I can write it as P I0 I1, or rather, so I want to take the expectation of this. So what is the expectation of this particular? So remember, I0 is equal to I. So how should I write the expectation? I'm going to write the expectation as follows. I have this big matrix P mu. I'm going to multiply it by C mu, and I'm going to evaluate it at I naught. So P mu is a big matrix, C mu is a vector. I multiply the matrix by the vector. I look at the I0th component. That gives me this particular. No, this okay, so this expression doesn't have P mu. So this is just C mu. This is just C mu of I naught. This is alpha P mu C mu of I0. This term is going to be alpha square P mu square C mu evaluated at I0. Okay, so this entire set of expectations that I was supposed to take, it's purely a function of matrix multiplied by a vector evaluated at a certain specific element, I0. Okay, does this make sense? So what we are doing is taking the expectation of the future cost conditioned on the current I0. So if you think about it, if you go back and think about it, it's going to actually be the matrix that gets multiplied by C mu. So let's see this particular expression. Let's see why this expression would give me this result. So we have this notation here, and I'm looking at alpha, expected value of alpha C I1 mu I1 and I2, given that I naught is equal to I. How do I compute this expectation? So that will be alpha summation I1 P I0 I1 mu I0, and then summation I2 C I1 mu I1 I2. So okay, so I think I need to have a P again here. So I have to take the first expectation with respect to I1, and then I need to take the second expectation with respect to I2. So I think this is correct. This needs to get multiplied to P I1 I2 mu I1. Am I right here? Am I making a mistake? Oh yeah, that's right. Okay, perfect. No mistake. What does this element inside, what does this look like? It looks something like this, right? So this is C mu of I1, and this is P mu, and I'm taking the average with respect to I1. So not the average, but I'm summing it up over I1. So this is the matrix, one row of the matrix getting multiplied by this entire vector, right? And that's where I get this particular statement from. Okay, so this one is P mu of I0. So remember I0 and I1. So I'm taking the sum over all I1, and this is just a C mu of I1. So what I really have to do is take the row vector of P mu, multiply it by the entire column vector C mu, and I get the ith element of I0th element of this particular vector. And that's exactly what I get here. So P mu times C mu multiplied by alpha is what the expectation of this term is going to be like. And by a similar argument, the expectation of this term is going to be alpha square P mu square C mu. Okay. What does that imply? So what that tells me is if I look at V mu of I, what I get is summation of alpha raised to t goes from 0 to infinity, P mu, C mu, this is evaluated at I. So the ith element of this particular matrix. It's actually going to be a vector, P mu raised to t. So this is a discount factor. This is a matrix. So it's a square matrix. You raise it to t, it remains a square matrix. It gets multiplied to a vector. So what you get is a vector. You are summing up infinite number of vectors. The vectors are going to 0 because alpha raised to t is taking that vector to 0. So this is actually summable, and I'm looking at the ith element of this particular vector. Okay, comes directly from here, from this expression. Any questions so far? No? So the way to evaluate a value, V mu, is by computing this matrix P mu, multiply it by a vector C mu, and then you take this summation over infinite number of time steps. So this is the policy evaluation step. This is how you evaluate the policy. If you were to evaluate the policy truly, this is the infinite sum that you really need to compute in order to evaluate the policy. Okay. Now this is the result that we need to prove. How do I prove this particular result? What do you think? How should we go about proving it? What is the cool property of this matrix. So we know that alpha is something between 0 and 1. What's the cool property of a transition matrix? So the rows sum to 1. What else? The rows are non-negative. Okay, so every element of this particular matrix, P mu, is non-negative. So this is greater than or equal to 0, and rows sum to 1. That's just by the definition of the transition kernel or the transition matrix. Okay, so this is going to be important to prove this result. What else do I know? So I know that mu plus is the argmin of this particular expression. So mu plus is argmin what does this imply? That C mu plus P alpha P mu plus V mu is less than or equal to V mu. So I'm replacing this U here by mu plus of I. Okay, and that's how I get that expression. Okay, so mu plus is the argmin of this particular expression. What that means is for every I, if I replace U with U star, remember this is argmin, so mu plus I is U star, then I'm definitely going to reduce the value with respect to V mu for every I. Does that make sense? Did I lose everyone? Yeah.
So the box is just a restatement of the theorem.
It's not really the theorem. The theorem is V mu plus. So V mu plus is this, replaced with plus everywhere.
Okay.
This one has V mu here. There is V mu here. So I'm just carrying V mu here. But what does mu plus? V mu plus satisfy? V mu plus satisfies two things. First is V mu plus equals summation or so this is what V mu plus is supposed to satisfy. And I'm proving that this is less than or equal to V mu. Okay, I'll just pause here so that you can assimilate this equation. But I definitely want you to be comfortable with the idea that I'm doing the argmin here, and that is equivalent. These two statements are actually equivalent. I mean, okay, maybe not equivalent, but I'm taking an argmin here, and I want to make sure that that particular statement holds. Maybe I shouldn't do it the other way. But yes. Yeah, this one. This one, this side. No, it should have a plus here. So remember, V mu plus is a fixed point equation. It satisfies the fixed point equation of the Bellman operator. I mean, not the, yeah, sorry, go ahead. This is the theorem. This is what we want to prove. No, sorry, this is not what we want to prove. This one implies this, and then I wanted to prove the rest of the result, but this is an intermediate question that came up in the class. Yeah.
Because, so I understand the left side of the box inequality is just rewriting
Right.
that with the mu plus.
Yes.
But then why do we have the inequality?
Oh, because you're taking the min. So what I'm saying is, let me erase this. All I'm saying is f of x star is less than equal to f of x. That's all I'm saying. So I have a function f. I'm minimizing the function. The point is x star at which the minimum is achieved. All I'm writing is f of x star is less than equal to f of x. Okay, that's all I'm saying. So let me unpack that. So I have summation pij mu plus I c I mu plus I j plus alpha vj is less than equal to v mu I. This is v mu less than equal to v mu I. Less than equal to c I uj plus alpha u with. That is the argument that I'm making.
So as I understand it, like you start with the left side of the inequality, you replace the mu pluses with mu.
Only this one, because here I have a v mu.
Right, but I'm saying like we can start with the left side.
Yes.
If we replace the mu pluses with mu, then it could get bigger.
It will definitely get bigger. Yeah.
Or equal.
It'll become equal to v mu because v mu is a fixed point of.
Yeah, so that's the
Yeah.
step that I was missing.
Yeah.
Is the
Yeah.
fixed one.
Yeah. V mu is a fixed point of. So v mu is evaluation of the policy. So if you replace mu plus with mu, this will be equality. Any other question? Any other question? No? Okay, so this is what I'm using here, and I'm going to erase this. And the clarification that Phil had was C mu plus alpha P mu V mu will be equal to V mu, right? Because V mu is a fixed point of this. It's the evaluation of the policy. So this, for every policy mu, this condition has to hold because V mu is given by this expression. Okay, so all of you agree with inequality number 1. Sorry, equation number 1 and equation number 2. So equation number 1 is inequality. Everybody agrees with it. Equation number 2 is an equality and everybody agrees with it. Right? Now I need to prove from starting from these two expressions, or maybe I don't even need this. I don't even need expression number 2. I start with expression 1. I need to prove this theorem. What should I do? Let's think about it. So I'm going to erase this side of the board. Okay. So I have C mu plus alpha P mu plus V mu is less than equal to V mu. Wonderful. So what do I have here? C mu plus alpha P mu plus C mu plus alpha P mu plus V mu is less than equal to okay, so I'm just using this inequality here. Why should this inequality be true? Why should this be true? So I know that V mu is greater than this particular expression. So I had V mu here and I replaced it with an expression that is element wise smaller. But why should have a less than equal to sign here? Yes.
So you're just replacing V mu with that.
With that expression again.
Then why does it have policy mu plus?
No, so remember I have this V mu is greater than this expression, right? So I'm going to replace this V mu with that expression, which is a lower bound, and I get this less than equal to sign with respect to this expression on the right, right? So I'm just replacing this term with something that's lower, smaller than that, okay, element wise smaller. But my question is, why do I have a less than equal to sign here?
All entries of the K is non-negative.
Yeah, all elements of this is non-negative, right? Remember we were talking about it. So all elements of this matrix is non-negative, as a result of which I replace V mu with something that is smaller than V mu, which is this expression, and I get this inequality here, okay? But guess what? I see V mu again here, okay? So I can replace it again, this V mu, with something that is smaller than V mu. So what do I get? C mu plus alpha square alpha cube what rings a bell? So I see some pattern that is recurring. So the pattern holds for k equals to 1. The pattern holds for k equals to 2. The pattern holds for k equals to 3. What do we do in these situations? We apply the principle of mathematical induction. So what I have is C mu plus alpha raised to t, P mu plus raised to t, C mu plus t equals 0 to capital T. Well, I know capital T is already being used for Bellman operator. What should I use? I'll keep using capital T for time as well. I'm going to run out of symbols pretty soon. V mu is less than equal to V mu. How about I use capital K? Are we using K somewhere? No, we are not using K, but let's use K then. This holds true for all K. This term is going to 0 because alpha is between 0 and 1. So alpha raised to k plus 1 is going to 0. This term is always bounded because V mu is bounded, and this term is between 0 and 1. So all the elements are between 0 and 1. So this term is bounded. So I have something going to 0 multiplied by something that is bounded. What happens if I let capital K go to infinity? I have V mu plus less than equal to V mu. Okay, and this is the one of the most foundational results in the context of RL, that every time you improve the policy with respect to a specific value function, you get something, you get a policy that is strictly better. I mean, maybe not strictly better, but it's definitely better than the original policy you started with. Okay, so in the entire reinforcement learning algorithm, whatever algorithms we will study, this is the result that we will always be using. Every time we pick a policy mu, we'll evaluate that policy. We'll do a one-step rollout. So this is a one-step rollout algorithm. We compute a new policy, mu plus. And because of this result, because of this theorem, we know that the value with mu plus is always going to be better than the value with mu. Always. Okay. Any questions so far? Every time you improve upon the policy, that stationary policy is going to be very good in comparison to the previous policy that you are using. And this is known as a one-step rollout. Yes?
Provide a real-world example about that.
Real-world example of this?
Yes, so policy update, which the application.
What's the application? So you look at the current policy that is being used to optimize the air conditioning system of this room. You compute the value function, you compute what it costs to use that policy. You do a one-step rollout and you figure out the updated policy. Okay, this is a one-step rollout. You use the one-step rollout to figure out the updated policy. You know that the total energy cost of this updated policy will be strictly better than the policy that you are currently using to cool down this room or cool down this building or heat up this building or whatever. Okay. Yes.
This is for finite MDP, right?
Right. This is for finite MDP.
Continuous state and space.
This statement still holds.
Still holds.
Yeah.
Continuous state and.
That's right.
Whoa.
Yeah. Except that, you know, we are doing this matrix multiplication stuff here. In the case of continuous state space, you will do what is known as linear operators, like positive operators. So each of this would become a positive operator, and then you are essentially applying positive operators to functions, and you get the same result. But because I don't assume functional analysis in this room, I'm not going to make that argument. But the same statement holds exactly, this particular theorem would hold exactly within this general framework, even for continuous state, continuous action setting. Yeah. Or general state, general action setting. Like you could even have abstract spaces and it will work in those cases. Okay.
I remember Saturn says that this for continuous state. I remember he says in his book, this may not be true. Saturn says so. Okay.
That's why we are not using Saturn's book. I mean, no. See, the thing is that a lot of these results can be proven with appropriate framework. Like, you know, so if you have, I know I'm digressing, but when you are in a general state space setting, your cost function might diverge to infinity, right? So if you have a quadratic cost function over a Euclidean space, it might diverge to infinity. So now you need to be able to control those terms that are going to infinity. So you need to make appropriate assumptions on the positive operator, that it has a Gaussian tail or sub-Gaussian tail. So even if the cost function goes to infinity, the sub-Gaussian tail is going to kill that that term that is going to infinity, and so all of these statements are going to be not saying that infinity is less than equal to infinity. So there is some. It's not all nice and cool. You have to be a bit careful when you are going to general state space setting, but you can still establish all of these results with appropriate assumptions on the operators. Yeah. Any other question? Yes.
So if we repeat this process, then we can get V mu plus is less than V mu plus.
V mu plus is less than equal to V mu. Yeah.
Yeah, and if we repeat this like literally using mu plus,
Right.
to obey that,
That's right.
we get, V mu plus.
Absolutely. So that's the ultimate result of policy iteration algorithm, right? So remember, we were doing this policy evaluation and then policy update. So we did the policy evaluation, we do the policy update, we get this result. Then we do the policy evaluation of mu plus, and then you get mu plus plus, and you get this result, and then you keep doing that, and you get to the optimal solution eventually.
In that case, can you prove the existence of some policy or implemented in the fashion in the value function?
Right. So the existence of the optimal policy is something that we do not see. It's a finite state space setting under fairly general conditions. For the discounted cost, we have proven that optimal policies exist, right? That was the second or the third class. So I think the existence part is already clear. All we have to do is figure out computationally how to get to the optimal policy. Okay, but for the infinite state setting, for the general state general action setting, proving that an optimal policy exists still remains a very difficult challenge. Like, we'll cover some of those challenges towards end of October, but for now we are assuming finite state space setting because everything is simple and easy to understand in finite state space.
Sorry, I just remember. Something says that doesn't say that for continuous space it is not. It says for function approximation, it may not hold.
That's right. With function approximation, things are a bit complicated.
So
Yeah.
So when with function approximation, it may hold with some probability, right?
That's right.
Okay.
That's right. And it depends on the expressiveness of the function class. So today the assignment is due, and the last problem of the current assignment is about using transformers, neural network, and XGBoost to approximate certain functions, right? And you will see that under certain, like if you pick the function approximator in a wrong way, you get pretty bad errors. But if you pick the right function approximator, you get pretty good error for the function that you are trying to approximate, right? So you have like a bunch of functions. You have polynomial functions, and then you have functions of multiple variables, and you have chaotic functions. So depending on different functions, you will have different approximating power of the function approximating class. That's the final. That's why I gave it in assignment 1, so that when we cover that topic in end of October, you will know what I'm talking about the function approximation property.
And for theoretical, if we want to improve it to the function approximation case, they build a probability estimate for this.
That's right.
Oh.
That's right. Yeah. Any other question? Yes.
So are there analogs for the total cost and average cost?
Yes. So so there are policy iteration algorithms even for total cost and average cost setting. It's just that we won't cover that in the class. Yeah. But it's there in Bertseker's book. It's not there in other books, but in Bertseker's book, he goes deeply into some of these topics. Any other question? Okay. So we covered one of the main results of policy iteration algorithm, that the updated policy is always better than the previous policy that you started with. Let me erase this side. So let's talk about what the policy iteration, the original policy iteration algorithm is. Probably from 1960s, if I'm not mistaken, but I could be wrong. Policy iteration algorithm. So you start with mu naught, you get v mu naught, then you apply the policy improvement step, I want to give it a name. Should I give it a name? I should probably give it a name. Okay. So I'm going to define an operator M on a value function space, and this maps M goes from the value function space to policy space, and MV is equal to mu, and this is given by mu I is equal to argmin u in ui c plus alpha v. Okay, so I'm just defining an operator. It takes as input a value function, does this one-step rollout, and computes the policy mu that is optimal for that particular one-step rollout. Okay, because I'm going to be using this going from value to the policy space quite often in this and the next lecture, so that's why I want to give it a specific name so that it becomes easier to write that again and again. Okay, so what is policy iteration algorithm? Then you get mu1 equals to m v mu naught. Then you get mu2 is equal to m v mu1, and so on. That's the policy iteration algorithm. Start with some policy, get the value function, then update the policy, then get the value function, then update the policy, then get the value function. What's the drawback with this algorithm? Why should I not use this algorithm? Yeah.
Takes a long time to gather.
Right. So remember that V mu is an infinite sum. So you need to compute the infinite sum and then you need to sum it up. So each step requires an infinite loop. Okay. And then you have to run many such loops. So it's a bad algorithm. This converges, but it's a bad algorithm. Okay. How do you want to improve it? So each steps take infinite iterations. I don't want to take infinite iterations. How do I improve it? Any thoughts?
Finite iterations.
Wonderful. So we'll take a finite number of iterations. Okay, so I'll compute V1 to be okay. I need to define another operator. I'm so sorry. T mu that maps Vs to Vs, and this is T mu of V of I is equal to, I don't know if I have done this before or not. So I take the value function and then use the policy mu to do this one-step update. That's my operator T mu. So the modified policy iteration says instead of computing this V mu naught, so remember V mu is equal to T mu infinity of any vector. So let me make it 0 vector because it doesn't matter what vector I pick. So this is the original policy iteration where I need to compute V mu from mu. I don't want to do this. So what I'll do is I'll pick Vk equals to T mu k minus 1, or maybe Vk minus 1 is this, Mk minus 1, Vk minus 2, and then mu k equals to M Vk minus 1. So I'm not doing infinite number of iterations, I'm doing finite number of iterations. And then I'm updating the policy mu k. Okay, so that's modified policy iteration. So in modified policy iteration here, I needed to take an infinite number of steps in order to compute this value function and then update the policy. Now I'm just taking mk minus 1 number of steps, getting the value function and then using that value function to update the policy. Okay, so I've reduced the computational complexity significantly. Yes.
But with the finite number of steps, is there a guarantee that we converge to?
Not in finite number of steps, but in infinite number of steps, you will converge to the optimal solution.
The ballpark in the finite number of steps?
I don't quite know whether there is a ballpark number or not. Okay, so most of these results are classical results and they are proven in limit. So as k goes to infinity, everything converges to the reasonable value. So these are classical algorithms. There is the third algorithm, which comes from 2012 paper, enhanced policy iteration. Enhanced policy iteration is, well, it's, I think, Bertsekas and you 2012. This paper is cited like 50-60 times, so there is probably a lot of innovations that can be done based on this algorithm. But I'm not sure why many people have not studied this algorithm. So this is probably the only class where this algorithm is being taught. But I do want to tell you why this algorithm is interesting. So I'm going to define two operators. So I have a function q that maps S cross U to R, and I have a policy mu u given I is greater than 0 for all u in ui. This is new. This is not v. Okay, so how do I differentiate between v and new? Okay, let me write it. This is new. In MATLAB, in LaTeX, you will write it as \new. It's not v. It's not the value function. So it gives for a given action, for a given state I, it gives a positive probability to all possible actions that are admissible at that particular state I. Okay, so I pick a policy new, I pick a function q, and I pick another function j that would map S to R. So it's similar to j mu, but not quite. So it lies in the value function space. And I define an operator f j nu of q, and it's a fairly long operator, ci uj plus So there are two algorithms related to this. 3A is qk plus 1 equals to f jk nu raised to mk qk, and jk plus 1 I equals to min so this is enhanced policy iteration number 1, and V is okay. So there is a very specific structure in this particular algorithm. So you need two sets of functions, q function and j function, and you need a policy nu, which you can pick arbitrarily. It doesn't matter how you pick nu. Okay, it's your choice, whatever works for you. So you pick nu, and you pick q and j, and you start from some value j naught and q naught, and then you keep updating qk and jk in this particular fashion. So what does 3a does? 3a says I'm going to compute qk plus 1 by taking mk iterations of this particular operator, and then I'm going to update jk plus 1 by minimizing the q function. Okay, so jk plus 1 comes from qk plus 1, and qk plus 1 comes from this particular operation applied mk times. Okay, so this reminds you of this modified policy iteration where we apply mk times the operator and then we compute the function. So that's reminiscent of that particular algorithm. 3b is a parallel update scheme where qk plus 1 is a function of qk and jk plus 1 is a function of qk. Okay, so you can parallelly update this in a separate machine and update this in a separate machine and then get them together. You get qk plus 1, jk plus 1, and then you can do the update all over again. Okay, so both of these are contraction operators over a specific metric spaces, as a result of which both these algorithms converge to the optimal solution. The optimal solution being you get qk star and jk star, you get q star and v star at the end of the iteration, and then you do one step rollout and you get mu star. Okay, so this one is called enhanced policy iteration by these two co-authors, and it was published in 2012. Not many people have studied it, so you are encouraged to use it in your research if maybe it is helpful. I don't know. Okay, it could be helpful. Yeah.
May I ask, what is the advantage of this method compared to modifying policy?
Yeah. So what is the advantage? So this one seems to I think the authors did mention about some advantages. I don't recall, but it's in the paper. It's a fairly long paper, but I think it has something to do with this algorithm is more stable than the modified policy iteration algorithm. Like it gets to the solution. So right now we are talking about the not deterministic setting, but we are talking about the setting where we know the cost function, we know the policy, we know everything. I mean, everything is known, and so we are just doing the computation. When you are doing the simulation, the modified policy iteration will have a lot more instability. It will oscillate a lot more. This one will not oscillate as much. I think that's the argument the authors were making in their paper. Okay, so definitely check out this particular paper to know more about why this is better than that. But it has more to do with the stability of the algorithm in the simulation-based algorithm situation. So not in this particular situation. In this situation, everything converges to the optimal solution in infinite time step. Okay. Any other question? Yes.
Also, the reason why modified full situation has some oscillation is that it's not like infinitely.
See, the oscillations happens in the when you are doing the simulations, when you don't know the cost function and don't know the transition kernel, then you have to do simulations in order to figure out what the Q function and the J function and the policy mu looks like. We haven't talked about it yet. We'll talk about it in the future. You know, how do you do the simulations when you don't know the cost function and the policy and the transition kernel? That's what reinforcement learning is about. So right now we are not talking about it. Okay. Any questions? Okay. So we have the policy iteration algorithm, the vanilla policy iteration, then we have modified policy iteration. We don't want to take infinite number of steps, so I'm going to do this. Then we have enhanced policy iteration where you have some more functions, some more complications, but seems to be more stable than the original policy iteration or modified policy iteration algorithms. And the fourth one is the TD lambda algorithm, which unfortunately I won't have time to go over today. But I will introduce the algorithm. That's the fourth algorithm for today. So lambda policy iteration. And it would be called TD lambda algorithm when we do the simulation based optimization. So in the lambda policy iteration, the idea is that, or the problem is your alpha is close to 1. So if alpha is close to 1, you need to take multiple of these steps in order to be able to compute Vk minus 1 reliably, right? Because when alpha is close to 1, it takes a lot more iterations to converge to the optimal solution. So the question then becomes, how do I get a policy estimate? Remember, there is an actor part and then there is so the actor part is easy, that's just the policy improvement part, but the critic part where you need to evaluate the policy, that takes infinite number of iterations. So we want to figure out how to manage that infinite number of iterations thing. Given that this entire information, this Vk or Vk plus 1 that I have found, I'm going to throw it away in the next iteration, right? So I don't want to get to Vk. I don't want to spend so much computational effort to go to Vk and just throw it out after the policy update is completed. Okay, so that's roughly the reason for studying lambda policy iteration. So here I have jk plus 1 equals to jk plus delta k. Once again, j is a function from S to R. So what is this delta k? So let me give you the expression. So I'm going to define dk ij to be c I mu k I j plus jk j minus jk I, and I'm going to define delta k evaluated at I naught as expected value of summation t equals 0 to infinity alpha lambda raised to t and lambda is something between 0 and 1. There should be an alpha here.
Should be
Yeah.
alpha on both of the changes?
No. This is the current estimate at I, and this is the one step future estimate, and then I'm taking the difference, and I get a what is known as a temporal difference. So this is the cost I'm going to accrue in one time step minus the cost that I'm currently sitting at, which is jk of I. And then based on this temporal difference, I multiply it by a discount factor, which is the original discount factor multiplied by an additional discount factor term lambda. Okay, lambda is between 0 and 1. Oh, 0 and 1, both of them included. So you can pick lambda equals to 0 or you can pick lambda equals to 1, right? So you get a whole class of algorithms. And this particular function is denoted by delta k. And so my policy evaluation step is I pick the previous vk and then I add this delta k term and I get jk plus 1 and I send the jk to the actor to evaluate, to come up with a new policy. Yes.
If there's an infinity in the sum, so.
Right. So in almost all reinforcement learning algorithm, we start with infinity in the sum. And then when we do the simulation, we'll stop the simulation at some point of time and just get along with it. Okay. So, which is true even in like gradient descent algorithms and so on. So you're supposed to do the iteration for infinite steps, but you kind of have a termination criteria after which you say, okay, I'm done. Like this is what it is. So we'll do that. Okay, so that's all. So I'm going to start from here in the next class and I'm going to tell you what exactly is this jk fixed point of. Okay, so that's the equation we'll derive, after which we'll get into reinforcement learning. So we'll talk about Q learning, simulation based optimization, and so on and so forth. So the entire lectures on the Markov decision processes is over, and now we'll talk about only simulations moving forward. Okay, thank you so much. See you in the next class.